In this video, we're going to be talking about several methods of how to solve for various unknown variables using some graphical methods and also just using some basic problem solving methods and kinematic formulas as well. So we're looking at a velocity versus time graph. So as I take a look at what I see right now, I have an initial velocity in the beginning of 3 meters per second because that's my y-intercept. And I also have a final velocity at the end of 21 meters per second and a total time of 12. So I'm going to go ahead and label some of those things. I have a total time of 12 seconds. I have an initial velocity of 3 meters per second because of my y-intercept. And I have a final velocity of 21 meters per second as well. Now, the first thing I'm going to do is use a graphical method and then solve for the acceleration. So if I'm taking a look at a velocity versus time graph, the way I would do that is find the slope of the line. And I'm going to go ahead and use my y2 minus y1 over x2 minus x1. And that's going to give me my slope, which is my acceleration. So I already have my first and last value marked on the graph over here. I'm going to go ahead and call this one my x1 and this one my y1 and this one my x2 and y2. So I'm going to be careful labeling those so then when I put them into the formula, they'll all fall into the correct position. So I'll calculate the answer as accurately as possible. So I got 21 minus 3 over my x2 of 12 minus 0. And that equals 18 meters per second of velocity divided by 12 seconds. And that equals 1.5 meters per second squared for my acceleration. So that's the graphical approach to it. Now, what I'm going to do is show you a second approach, which is basically using a kinematic formula as opposed to using the graphical method. And you're going to see both end up being very, very similar to one another. So if I use the kinematic formula delta V, which is final velocity minus initial velocity over time equals the acceleration, I can also find the acceleration that way. If I do that, I'm going to have acceleration equals my final velocity of 21 meters per second minus my initial velocity of 3, and then divided by my total time of 12, and then I end up getting 18 meters per second up top, 12 seconds on the bottom, and I come up with the same value of 1.5 meters per second squared. Okay, as you can see, the way they work out mathematically is very, very similar. It's just your perspective and approach to the problem. So oftentimes people become comfortable with doing word problems, labeling variables and putting things into formulas. If you like that method, then I would label all of your known variables in blue just like this, and then put it into a kinematic formula, and then that will give you the acceleration. If you're more comfortable with the graphical methods and you like finding slope as opposed to using the kinematic formulas, go ahead and use that approach too, and use the y2 minus y1 over x2 minus x1 method, and then you'll still get the same final value of 1.5 meters per second squared. All right, so let's go ahead and move into a couple different tips and tricks. The next one is we're going to use the graphical method to solve for the delta x. Now, to find the delta x on a velocity versus time graph, we want to find the area underneath the curve. And the way we're going to do that is we're going to break it up into two sections. We have basically a long, skinny rectangle over here. And then we also have a right triangle as well. So I'm going to find those two areas, and it looks like my long rectangle is 12 wide and then goes up 3. So 12 times 3 is going to give me 36 meters. And then for my purple section, I'm going to do 1/2 base times height. 1/2, my base is still that 12 second width over here. And then my height is from the 3 up to the 21. So then my height is 18. So 1/2 base times height is 12 times 1/2 is 6. 6 times 18 is 108. I'm going to go ahead and add those two together. And then I get 144 meters for my delta x. So that's a graphical method. You're basically looking at the area in between your curve and the x-axis. So it can dip underneath and give you a negative delta x, showing you that you're moving back in the other direction. Now, if I want to use the kinematic method, I would use something like this. I would go ahead and write down all my known variables and then plug things in. So if I were to use this formula, I could just as easily get the same solution. So my delta x equals by VI, which I know is 3 meters per second, because that's my y-intercept. My total time is 12 plus 1/2. I now know my acceleration is 1.5, and then my time is still 12. I'm going to go ahead and square that. Okay, so the 3 times 12 is 36, just like this orange value right over here. And then if you take 1/2 times 1.5 times 144, which is 12 squared, you actually get 108. And of course, if you add 36 and 108, as you did the first time, you still get 144 meters. All right, so there's two approaches to getting your values that you're looking for. Some of the values you're looking for might just be directly written on the graph, like your VI, your VF, and your T. Other things, you might have to use the slope or the area between your line and the x-axis. But then also, the method that a lot of people may not think of is using kinematic formulas, writing down their variables and then plugging them into the formula. So if that's where you're comfortable, go ahead and use that method and you'll still get the same values. And sometimes you could even use both to kind of double check your work and see if those match up. And if they do match up, then you're definitely doing something right or a lot of things wrong, but very likely both of them are correct. So I hope that was helpful to you. Thank you for watching and listening.